Okay, now that we've sort of introduced power series, and we've done a little bit with them, namely finding radius and interval of convergence, and knowing the three different varieties that we have there, whether converging at a point, converging at a finite interval, or converging everywhere. We're going to go on and we're going to discuss manipulation of known power series. Now, obviously at this point, the only one that we are really familiar with, okay, is the fact that f of x is equal to 1 over 1 minus x can be represented as this power series, right? And that just winds up being, x to the n. Well, if that can be represented, then we should be able to represent functions that are similar to that if we can just squeeze them into sort of this mold, okay? So what if I'm instead given g of x as 1 over 1 plus x? Well, Well, doesn't that just give me 1 minus negative x? So could I actually just represent that as 1 plus negative x plus negative x squared plus negative x cubed plus, well, and of course every odd degree will turn negative and every even degree will remain the same. And so what I have here is negative x to the n. Or, if you choose to sort of split out the alternating, that would be negative 1 to the n times x to the n. So we should be able to, with a little bit of finagling, figure out how to fit that in, okay? And now here's the thing. It has to be in that form right there. The only thing that's negotiable is what goes in for x. There can be an expression there in terms of x, but we need that to be 1 and we need that to be 1. Okay, this first one was a little bit easy. Let's move on to one that is perhaps a little bit more difficult. Let's say that we're given 2 over 3 plus x. Okay, well, I need to get at least, let's get the numerator, okay, as a 1. That's a good first step. Let's just pull out the 2. How am I going to get that to be a 1? Well, what do you say we multiply by 1/3 over 1/3, okay? And if we multiply by 1/3 over 1/3, 1/3 over 1/3, we're going to get 2/3 out in front, okay? And we're going to get 1 plus x over 3. Okay, well, we're not done yet. Let's go ahead and keep that 2/3, okay? 1 over 1 minus negative x over 3, and now I'm getting somewhere, okay? Now, this 2/3 can actually remain up here if you want. I was actually just trying to evacuate it so you see the 1 and the 1. All this winds up being is a common factor which is distributed across every term of that infinite polynomial. Okay? The polynomial with infinite number of terms or whatever. There are a lot of people who would take issue with the way that I'm describing it like that, but you know me, I tend to play fast and loose when I think that something is descriptive, even when it's not technically by definition correct. It's rather descriptive. A power series just kind of looks like a polynomial with infinite number of terms. And of course, in order to be a power series and be able to be written in sigma notation, that infinite polynomial has to have, each successive term has to have a pattern, right? Remember, the sequences and series are strings of numbers with a discernible pattern. A power series is an infinite polynomial where each term, there is like what happens between each term winds up being a discernible and therefore a representable pattern. Now what happens here is this can wind up being sigma as n is equal to 0, okay? And we can put the 2/3 in here and then negative x over 3 to the n. Now, this, you can change this and it can wind up, you can pull the 2/3 out in front if you want, and you can do the -1 as a separate thing, because some people just, when they're dealing with an alternating series, they like to see that -1 right there to the n, or -1 to the n plus 1, depending on whether you start with a positive or a negative term in that power series. They like to see that -1 pulled out and to be sort of alone, to sort of show you the alternating nature of that power series. But that actually should be it, okay? And actually, if you wanted to write out some of the terms and actually see them, you could put the 2/3 out here if you wanted to. And of course, the first term would be plugging in 0, so it would just be 1. And it'd be negative x over 3 plus negative x over 3 squared plus negative x over 3 cubed. And that would basically be the sort of written out, the longhand version of what you've represented in either one of those sigma notations right there. And, if you wanted to, if you were asked to, you could find the interval of convergence and the radius of convergence for for one that's sort of based upon the geometric. It really isn't that big of a deal, right? It's just negative x over 3 has to be less than 1, right? Whatever is right here, whatever that ratio is right there, whatever goes in for what used to be that r has to be less than 1, okay? Which means that absolute value takes away the negative, and so you wind up getting x over 3, and therefore it's -3 to 3. Obviously, the radius of convergence is 3. This is the interval. You don't have to check the endpoints because, like I said, it's based on the geometric, and the endpoints will not satisfy. It's kind of what's nice about the manipulation of existing power series. You can take sort of that knowledge with you as you sort of move along. But that would be the interval if you were asked for it, okay? But right now we're not so much interested in radius and interval of convergence. We are interested primarily in just manipulating an existing power series. Now this was basically just a little bit of moving around terms and factors and stuff like that. Let's go ahead and move on to something a little bit more robust and a little bit more, calculus-ish. And let's see if we can figure out how to get at 1 plus x squared. 2 over 1 plus x squared. Now, that is a little bit trickier. And the reason it's a little bit trickier is you sort of recognize the fact that if I had y is equal to if I had y is equal to 1 over 1 plus x, that would be 1 plus x to the -1, and y prime could be negative 1 plus x to the -2, or -1 x plus 1 squared, or 1 plus x squared. Will this knowledge help us? And the answer is yes. Because you can differentiate or integrate power series term by term. And let me show you what I mean. Obviously, if you have y is equal to 1 over 1 plus x, that is 1 minus x plus x squared, minus x cubed plus x to the 4th plus, We've already seen that one, right? And so if you did y prime, that winds up being -1 over 1 plus x squared. That winds up being 0 minus 1 plus 2x minus 3x squared plus 4x cubed minus 5x to the fourth, right? So there's still a discernible pattern. Could I then factor out, or could I then basically, okay, let's sort of scratch the fact that that's y prime, and let's just play with this right here, okay? Could I turn this into this by multiplying both sides by a negative? And I wind up getting 1 minus 2x plus 3x squared minus 4x cubed plus all the way out. Sure. And now can I manipulate this? Can I change both sides by multiplying both sides by a 2? Now, this should look awfully familiar. This is this. Okay. Well, here's the question. What happened to the sigma notation while I was doing all of that? Okay. Now, I know that the original right here, okay, and let's actually start over with that. I know that the original right here, 1 plus x, is sigma n is equal to what? Well, right here, okay? We've already got that. So let's start off with that, okay? N is equal to 0 to infinity of negative 1 times x to the n. Now then I took the derivative, right? I took the derivative and I wound up getting that. Well, what do you suppose happens when I take the derivative? Well, obviously nothing happens to the sign, S-I-G-N, right? But you just basically do the power rule of differentiation, and you wind up with that. Okay, well, what happens when I multiply through by a negative? You're not changing the alternating nature of the series. You're simply changing which term, right? So the only thing that multiplying both sides by a negative should do is it should, and I'm just going to swap the places of these two. Multiplication, after all, is commutative. And I can go ahead and we'll put n plus 1 right there. And all that does, going from negative 1 to the n to negative 1 to the n plus 1, all that does is it changes which term winds up being negative. And then if I want to multiply by 2, I simply get n is equal to 0, sigma 2n, negative 1 to the n plus 1 times x to the n minus 1. And that is the power series. Okay? Now all I've done here is, instead of manipulating the infinite number of terms, term by term, to actually show how that recognizable pattern changes from term to term, I've simply done it within the sigma notation and manipulated my a sub n. Okay? But it basically winds up being exactly the same thing. Okay? Does this right here represent the same thing that this does right here? Let me go ahead and just fold that over so you can actually look at them. Okay. Do those represent the same thing? Well, just plug in first couple of numbers. Plug in n is equal to 0. Okay. Well, if you plug in n is equal to 0, obviously the first term is going to be 0. Okay. If you plug in 1, okay, you're going to get 2. You're going to get a positive 1 here, and you're going to get x to the 0 here. That is going to give you a 2. Okay. Let's go ahead and go to the next term. Plug in n is equal to 2. Well, you're going to get 4. You're going to get negative 1 to an odd power, so it's going to be negative, and you're going to get x to the 2 minus 1, or x to the first, so you get x. This actually does represent this infinite string of terms, right? As long as it has a pattern, you should be able to actually represent that pattern in terms of the power series, and that's exactly what we've done right there, okay? Now, The only thing you need to remember is that when you take the derivative or integrate a known power series, the radius of convergence remains the same. The interval, however, might change because the endpoints might change, okay? So all you have to do in order to check the interval of convergence for a power series that you've basically derived by either integrating or differentiating a known power series is just recheck the endpoints to determine whether the interval of convergence is inclusive or non-inclusive on either end of the interval, okay? That brings us to about 16 minutes, so let's go ahead and call it quits on this one. We'll go ahead and continue to play with manipulation of power series into the next video. We'll probably wind up only having two for this particular section. Despite the fact that it winds up being a rather important and a robust one, there's only so many examples before you kind of go, yeah, I got it. 11.10, we'll figure out exactly how many we need when we get there. But if you have any questions, as always, please do email me. And like I said, on top of the fact that your teacher's not going to be spending that many days on 11.8 through 11.10, and therefore she can't get into much that is in depth, we will shore up the rest of this and sort of gain a more robust understanding of this as we venture into the AP questions that are asked about this topic. And that'll help us take what is sort of undeveloped sort of understanding and develop it further such that we really have a handle on these power series, and of course moving into 11.10 both Taylor and Maclaurin series as well. So email me with any questions. Bye.